Guys, sorry about canceling a live conference today at 11 o'clock. I'm having some internet troubles. So what I'm gonna do is I'm gonna shoot this video, then I'm gonna upload it to my YouTube channel, and then you guys can access it from there, okay? So today we're gonna do 9.2, which is simplifying radicals. Now we've gone over square roots already of perfect squares. The square root of 16 is asking what number being multiplied by itself will give me 16. And we know that that's 4, okay? And just to go over again real quick how to find a square root in your calculator. On the TI-30X2S, if we want to do square root, we hit second, the x squared button, then we type in the value. That's the square root of 16 equals. Let's try our next example. The square root of 81. Asking what number being multiplied by itself will give me 81. Second, the x squared button, 81 equals. So you can see the square root of 81 is 9. Now those two examples are nothing new. We've already gone over how to take the square root of perfect squares. Today we're going to learn how to take the square root of things that are not perfect squares. So let's take a look. If I asked you guys to take the square root of 20, 20 is not a perfect square. There is no number that when you multiply it by itself that will give you 20. But that's not in simplest form. If I did the square root of 20 in my calculator, I would get 4.47213595, and it would go on forever. So this is actually an approximation. When we're dealing with simplifying radicals, we want exact answers. Okay, so there's something we can do. We can break this square root of 20 down into the product of two factors. And we want one of those factors to be a perfect square. So think about it. Our perfect squares are 1, 4, 9, 16, 25, 36, and so on. So we can break this square root of 20 down into the square root of 4 times the square root of 5. The square root of 20 is the same thing as the square root of 4 times the square root of 5. The square root of 4 is a perfect square, so I take the square root of 4, which is 2. So 2 times the square root of 5 is my simplified answer. That's my exact answer. So if I did 2 times the square root of 5 in the calculator, 2 times the square root of 5 equals, I guess this is exact decimal that we got. But again, this is an approximate answer. We want an exact answer. So I was able to break down the square root of 20 into two factors where one of them was a perfect square. Okay? This rule, where you can break the square root of 20 down into the product of two factors where one of them is a perfect square, that's called our product rule. Okay? So let me explain that real quick. So our product rule states this. Our product rule says that if you have the square root of a times b underneath your radical, you can break it up into the square root of a times the square root of b. That's our product rule, and that's what we're going to use to simplify these square roots that are not perfect squares. Okay? So let's do a couple examples now. Okay? Let's try the square root of 200. Again, 200 is not a perfect square. If I do it in my calculator, second x squared 200 equals, I get a decimal. It goes on and on and on and on and on. Okay? Well, we want an exact answer. So think about this. What could I break 200 down into to where I have a perfect square that goes into it? Well, I know 100 is a perfect square. So I can break down the square root of 200 into the square root of 100 times the square root of 2. And now I know that this square root of 100 is a perfect square. So the square root of 100 is 10. I have 10 times the square root of 2, or 10 radical 2, as my final answer. And if I were to multiply 10 times the square root of 2, I would get the exact decimal that I got if I did the square root of 200. But this answer is an exact answer, and that's what we're looking for. Let's try one more. Square root of 12. 12 is not a perfect square. 3 times 3 is 9. 9 is a perfect square. 4 times 4 is 16. 16 is a perfect square. But what I can do is I can use that product rule we just learned. And I can break 12 down into the square root of 4 times the square root of 3. And I know that the square root of 4 is a perfect square, which is 2. So I get 2 times the square root of 3. And both of those answers are exact answers. And that's what we're looking for. So I want to do one more example just to show you. Some people don't split up the product rule into 2 square roots. Let me show you what I'm talking about. The square root of 54. We'll use our product rule. Let's break it down into the square root of 9 times the square root of 6. So some people, rather than break it up and do the square root of 9 times the square root of 6, will write it like this, where you have both factors underneath the radical. And that's fine if you do it that way. But just know that when you take the square root of 9, which is 3, that 3 comes out front of the radical. So we get 3 radical 6, or 3 times the square root of 6. Okay? So it doesn't matter if you break up the square root of 54 and write it like this. Now take the square root of 9, which is 3, multiply it by the square root of 6. You see we get the exact same answer. So if you do write both of them underneath the square root, make sure when you take the square root of that perfect square that that value comes out in front of the square root. Okay? That's very important. So again, we're using the product rule to split these up to find a value that's a perfect square that goes into it, okay? Let's try another one. Three times the square root of 8. Well, the square root of 8 we know can be broken down into 4 times 2. And now underneath my square root, the square root of 4 is a perfect square. The square root of 4 is 2. So we're going to take the square root of 4, which is 2, and we're going to move it out front. But when I move it out front now, I have to multiply the 2 times 3, which gives me 6. So I took the square root of 4, which was 2, brought it out front, multiplied it by 3 to get 6. So my final answer is 6 times the square root of 2. Now, what happens when we have fractions inside of our square root? We've gone over this. If they're perfect squares, it's no big deal at all. Okay? If I have a fraction underneath our square root, there's a rule that states that we can write this as the square root of 9 divided by the square root of 16. This is called our quotient rule. So we had a product rule where we broke it up into the multiplication of 2 factors. And we have this one, which is called the quotient rule, which states we can write it as the division of 2 radicals. The square root of 9 is 3, over the square root of 16 is 4, to get 3/4. Same thing applies. If we have what is underneath the square root, and it is not a perfect square, we're going to do our same thing. Let's try one of those examples. Okay? So let's say we wanted to simplify 3 over 64. The square root of 3 over 64. Our quotient rule says that we can split these up and do the square root of 3 divided by the square root of 64. Well, the square root of 3 is not a perfect square, and we can't break it down with the product rule. It has to stay as the square root of 3. But we can take the square root of 64, which is 8. So my final answer is the square root of 3 divided by 8. Let's try another one. Let's try the square root of 40 divided by 81. Our quotient rule says we can break this up into the square root of 40 divided by the square root of 81. Think about it. What perfect square do you know goes into 40? Well, I know 4 does. So I can break that 40 down by using our product rule and doing the square root of 4 times the square root of 10 over the square root of 81. Okay, we're not done yet. Look underneath my square root, my radical here. The square root of 4 is a perfect square, which is 2. So we're going to bring that 2 out front and write 2 square root of 10 over, and we know that the square root of 81 is 9. So my final answer is 2 times the square root of 10 over 9. So notice, I broke this up and made it the division of 2 square roots. That's my quotient rule. Then I broke down the square root of 40 into my product rule. I took the square root of 4, which was 2, brought it out front, took the square root of 81, which was 9. This is my final answer, 2 square root of 10 over 9. So we have a product rule, we have a quotient rule, okay? What happens when we have some variables underneath here? Let's see what happens then. Okay. So take a look at this. We're trying to find the square root of x to the 5th power. So it's asking what times itself can give me x to the 5th. Well, man, if I do x squared times x squared, it gives me x to the 4th. If I do x cubed times x cubed, it gives me x to the 6th. So this is not a perfect square. But, and this is the hardest part for students to understand, you can take the square root of any variable raised to an even exponent. But this one is an odd exponent. So we have to break it down by using the product rule. And we have to break it down to where we subtract 1 from the exponent, x to the 4th times x. And you guys know from way back when, x to the 4th times x is x to the 5th. So I just broke the x to the 5th down into the product of 2 of its factors. But guess what? Now that this one has an even exponent, it's a perfect square. I can take the square root of x to the 4th, which is x squared. So I bring that one out front. Unfortunately, this x has to stay underneath the square root. My final answer, x squared times the square root of x. So the moral of this question here is you can take the square root of any variable raised to an even exponent. So if it's raised to an odd exponent, subtract 1 and multiply it by the other base. Now this will be a perfect square. Take its square root and bring it out front. Let's try one more example. The square root of 8y squared. Let's focus on the square root of 8 first. We can break the square root of 8 down into the square root of 4 times 2 times y squared. I used the product rule and broke the 8 down into 4 times 2 because I know 4 is a perfect square. So now I can take the perfect square of 4, which is 2, bring it out front. And it now leaves me with 2 times y squared. Well, I also just learned that y squared is also a perfect square because it has an even exponent. So all I got to do is divide the exponent by 2, and that's what its perfect square is. So it's asking what times itself will give you y squared. it's y. So the square root of y squared is y. So bring that y out front. My final answer is 2y times the square root of 2. I'm going to do one more example, guys. Okay, let's try this one. The square root of 45 over x to the 6th. Keep in mind, we have a fraction underneath our radical here. I can use the quotient rule and break it up and make it the square root of 45 over the square root of x to the 6th. Okay? Think about what perfect squares you know go into 45. Well, I know 9 does. So I'm going to break it down into the square root of 9 times 5 over the square root of x to the 6th. The square root of 9, that's a perfect square, is 3. So bring the 3 out front. So I get 3 times the square root of 5. And in my denominator, the square root of x to the 6th, since it is an even exponent, it is a perfect square. So all I had to do is divide that exponent by 2. My final answer, 3 times the square root of 5 over x cubed. And I want to do one final last example with a few extra variables in here. And then we'll call it quits. Take a look at this one. The square root of x to the 6th, y to the 7th, z to the 9th. Okay? We learned that when a variable is raised to an even exponent, it is a perfect square. So the square root of x to the 6th is x cubed. So that x cubed is going to come out front because it's a perfect square. These other two here are not even exponents. So they're not perfect squares. So we need to use the product rule and split it up and subtract 1 from that and multiply it by y. Subtract 1 from that and multiply it by z. Y to the 6th times y to the 1st is y to the 7th. So I just broke it down. Z to the 9th becomes z to the 8th times z. So what happens now is even exponent, even exponent. So these two are now perfect squares. Let's take this one now. The perfect square will be y cubed. Bring it out front. Perfect square of z to the 8th is z to the 4th. Bring it out front. And you're left with on the inside y times z. Thank you, and I hope that helped you guys out. If you have any questions, please post it on Schoology. Thanks.